All right, so now we're recording the lesson. This is grade 12 chemistry, chemical equilibrium in our first official Zoom meeting. All right, so someone's just walking in the room right now, and I've got to warn them you can't be in the room with me as I'm recording because you're going to get feedback on your device. Next door in the lab, if you want to go there, that'd be great. All right, so here we go. So equilibrium. Equilibrium deals with reversible chemical reactions. Okay, so we saw that a little bit in our kinetics unit. At the very end, we talked about potential energy diagrams with a forward and a reverse reaction. So equilibrium is linked to that. So for equilibrium to exist, whether it's in chemistry or not, you have to have two opposing processes. So in chemistry, that'll be a forward reaction and a reverse reaction. And they have to be occurring at the same time. A non-chemistry example of that might be just filling a bathtub with water, but you didn't put the plug in the drain. So you have water flowing in from the faucet, and you have water flowing down the drain at the same time. Those are your two opposite processes. Equilibrium requires a closed system. So in the bathtub analogy, you can have water coming in from the faucet, you can have water going down the drain, but you can't have water splashing out of the bathtub, and you can't have water coming in except from the faucet. In a chemical reaction, a closed system might be an actual closed container, but it could also be just a beaker of water with something dissolved in it, a chemical reaction happening in the water. As long as there are no reactants and no products are able to get in or out, it's considered a closed system. So physical examples of this, if you have water beside you in a water bottle and the lid is on the water bottle, you have evaporating occurring. The water in the bottle is evaporating, but then you also have condensation. You have water vapor that's returning back to the liquid state. So those are two opposite processes. Ice water, if you have water at 0 degrees Celsius, then the ice that's present is melting. But if it's at 0 degrees Celsius, the water that's there, the liquid water, is also freezing. So those are opposite processes. If the two opposite processes, this is the most important idea at the bottom of the slide, if the two opposite processes are happening at the same rates, okay, then you have equilibrium. So equilibrium is the point when the rate of the forward reaction in a chemical reaction is equal to the rate of the opposite reaction, the reverse reaction, or when the rate of one process is equal to the rate of the opposite process, you have equilibrium. If you think back to the bathtub example that we just mentioned, if you were filling the bathtub with water while at the same time it was draining down the drain, if you were filling faster than it was draining, then the tub will slowly fill up. But on the other hand, if it were draining down the drain faster than you were filling from the faucet, then the tub would actually drain downwards. It wouldn't fill up. But if you could adjust the faucet so that the water flowing into the tub was flowing in at exactly the same rate that the water was also draining down the drain, then the level of water in the tub would stay constant. You would have reached an equilibrium position. Okay, so equilibrium, the rates of opposite processes are equal. Now, when you have reached that equilibrium point, somebody who's looking at the system from the outside, they would say that it looks like everything has stopped. Okay, so if they couldn't actually see the water coming out of the faucet or the water draining down the drain, if they were just looking at the level of water in the tub, they would see that the level of water stopped changing. So they might assume that the drain was plugged and that the faucet was now turned off since the water level isn't changing. In a chemical reaction, maybe a better example, if you were watching a reaction happen in a test tube and suppose it was turning darker blue color, it was turning blue color. As long as the color is still changing, if it's getting darker and darker blue, then you know that the reaction has not reached equilibrium. But once it reaches equilibrium, then the blue color will stop getting darker. It will stop getting lighter. If it were getting lighter, the blue color would stay constant. So when everything appears to have stopped changing, you've reached equilibrium. But the key word there was appears, okay? The reactions never stop. Going back to the bathtub example, even though it looks like the level of water is holding steady and you might think that there's no more water coming out of the faucet or going down the drain, we know that the way we described it, water is always coming out of the faucet and water is always going down the drain. So although it looks like the process has stopped, it never actually stops. So we often say that it's a dynamic equilibrium. The word equilibrium implies it looks like nothing's happening. It looks like everything's balanced. But the word dynamic in front of that sort of suggests that even though it looks like everything stopped, at the molecular level, at the atomic level, at the particle level, things are always happening. So reactions are always going on, even though it looks like nothing is going on. Okay? So we say that equilibrium is a dynamic system. If you think of that water bottle, you can see in the pictures here, there's flasks with water in it, and the flasks are stoppered. So you have a water bottle with the lid on. You might say that the water inside that bottle is not evaporating anymore because the level is constant. But that's not true. The water in a closed water bottle is always evaporating. So particles of water are always leaving the liquid, as you can see in the flasks, and entering into the vapor phase. Then why doesn't the level of water drop down if the lid is on the bottle? Because the gas particles, the water vapor particles, are also condensing. And when they evaporate from the liquid and condense back to the liquid at the same rates, the level of liquid inside the bottle doesn't change. And somebody looking at the bottle would say the water's not evaporating. Now, if you take the lid off the bottle, then what happens is the water vapor escapes from the bottle. And in that situation, the rate of evaporating will always be greater than the rate of condensation, because the vapor is escaping. The condensation rate will be almost zero. So in that situation, it'll just keep evaporating, and there'll be no more water left if you leave the lid off. Put the lid back on, and suddenly the vapor increases in concentration. Condensation starts happening. The rate of condensation becomes equal to the rate of evaporation, and you've reached equilibrium. So in chemistry, in grade 9, grade 10, grade 11 chemistry, we only think of reactions happening as reactants becoming products, right? We think of the reaction as being only a forward direction. But in fact, most chemical reactions are reversible. If you put hydrogen molecules and oxygen molecules together, they will react and create water vapor. But as soon as water vapor is created, water molecules will decompose back into hydrogen and oxygen gases. So most, not all, but most chemical reactions can be reversible. Reactants become products, and those products become reactants again. All right? So once the particles have formed among the products, there's nothing to stop them from continuing to make reactants. Now, I just got a note saying that I cannot be heard. So I'm going to just double check my microphone and make sure that we are good to go. So according to my microphone, things are good.
Yeah, I can also hear you.
You guys can hear me?
I can. I don't know about everyone else.
I can also hear you.
I can hear you.
So that's their problem.
Okay. So Beatrice, if you could just check your settings. There seems to be maybe an issue with you, but my own microphone shows that it's working, and I think everybody can hear me as well. All right. Thank you guys for letting us know. All right. So as I mentioned earlier, the point in a chemical reaction now, where not a physical example, but a chemical example, where the rate, this is the most important idea in this introductory lesson, when the rate of the forward reaction becomes equal to the rate of the reverse reaction, then that reaction has reached equilibrium. And we say that it's reached chemical equilibrium. Now, why is that so important? That's important because it means there'll be really no more net production of product. There'll be no more net loss of reactants. Reactants are always getting used up to create products, but now the products are breaking back down into the reactants at the same rate. So all concentrations in the container would become constant. All the color would stop changing. The temperature would stop changing. The pressure would stop changing. All the different things you might measure about the container would stop changing. It would look like the chemical reaction has stopped. In fact, it hasn't stopped. It's simply reached equilibrium. Okay. Oh, I forgot to click and get these motivating little bouncing bullets. Okay, thank you, Microsoft PowerPoint. All right, now let's get a little bit mathematical. Okay, so far we've just been talking conceptually. Let's get mathematical. Write that title, the equilibrium expression, and then let's write this chemical reaction down. So hydrogen gas, H2 gas, reacts with iodine vapor, I2 gas. And you'll notice now we're using a double arrow. Instead of just a single arrow, we're using a double arrow, forwards and backwards arrow. That implies a reversible reaction. Okay, so I'm going to almost always at this point start using those reversible double arrows to indicate that we have an equilibrium system. The products of this reaction are two HI molecules, and those are also gas. Now, one little piece of vocabulary that's not here on the slide, since all the reactants and products of this reaction are gaseous, this is referred to as a homogeneous equilibrium. Okay? Homogeneous or homogeneous equilibrium, because everything is in the same phase, they're all gases. If everything were aqueous, that would also be a homogeneous equilibrium. Okay, so if everything is the same phase, it's homogeneous. If there were solids and gases, then that would be a heterogeneous equilibrium. And we'll deal with those later on. So now we're just looking at a homogeneous equilibrium. Hydrogen and iodine makes HI. When the system reaches equilibrium, there's a certain ratio of products to reactant concentrations, which becomes constant at any given temperature. Okay, so this constant depends on temperature, sort of like rate constants depended on temperature. Now, when we did rate constants, we used a little k to represent the rate constant. This is going to be referred to as the equilibrium constant, and to distinguish it, we'll use a capital K. So write a capital K. And you'll notice in the expression on the right-hand side, I'm using square brackets around everything. The square brackets implies that we're writing the expression using concentrations. Okay, so there is another version of the equilibrium expression where you use pressures when gases are available. Okay, I see William has raised his hand, so I'm going to pause and acknowledge William. Yes, William.
Mr. P, but the hydrogen, there's no square on it. You said that.
Yes, I'm about to explain that. Okay, so
Okay.
just copy this, and in a moment I'll explain why some things are squared and some things are not. Okay.
Okay, thank you.
All right. So because we are using concentrations in this expression, we call it a Kc. If this were an AP chemistry class or university, you would also deal with something called a Kp, where you use pressures. Some textbooks simply say K, so if you see K, you'll assume it means Kc. Sometimes they'll write K and then put EQ, EQ for equilibrium. It still means Kc. So whether you see just a K, a Kc, or a KEQ, you'll assume those all mean the same things. All right, now in this expression, William has noted that the HI's concentration is squared while the hydrogen and the iodine are not squared. So let's see why that is. Okay, so when the Kc, as I mentioned, is an equilibrium constant. The expression is always written for the forward reaction unless you specify that you're talking about the reverse reaction. So in the forward reaction, if you look up at the top of the screen, the HI is the product, and the H2 and the I2 are the reactants in the forward reaction. So given that, notice that the products are always written in the numerator of this expression. So HI concentration was on top. The reactants are written in the denominator of the expression. So the H2 and the I2 concentrations were on the bottom of the expression. Notice too, when there's more than one concentration, so there's an H2 and an I2 concentration, they're multiplied together. So in the denominator, it's the concentration of hydrogen multiplied by the concentration of iodine. Finally, why was the HI being squared, but the H2 and the I2 were not being squared? That's because of the coefficients in the balanced equation. When you look up top, the coefficients for the H2 and the I2 in the balanced equation were both 1s. So down in the expression for Kc, the exponents for H2 and I2 were both 1. On the right-hand side of the equation up top, the HI's coefficient was a 2. So down in the Kc expression, the HI's concentration is being squared. So the exponents in the Kc expression come from the coefficients in the balanced equation. Now, if you stopped and thought about that mathematically, there's an important point about that. It means that if you balance the chemical equation in a different way, if you were to double all of your coefficients, then all of the exponents in the Kc expression would be doubled also, and the value of the Kc would change also. So the Kc's value is always tied to a particular balanced equation. Right? It's also dependent, of course, on temperature. So the Kc value depends on temperature. That's the only laboratory condition that would change Kc. But Kc is also based on the way you balanced your equation. Okay? All right, hope that makes sense. If there's something that doesn't make sense, feel free to raise your hand or just ask me a question with your audio. I see somebody sent me a message here. So someone just asked, sorry, why are the products in the top and the reactants on the bottom? All right, so the question was, why are the products on top? That's simply the definition of Kc. So by definition, when we write a Kc expression, concentration of products from the balanced equation, they go on top. The concentration of reactants go on the bottom. Okay, William, I think your microphone is active. Unless you have a question, if you could mute your.
Okay, I'm sorry. My question is, so if the coefficient was 3, would like let's say 3 for the product, would that be like the product then cubed?
Yes, it would.
Okay.
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 So the person who is asking about why the products are on top and the reactants are on the bottom, there's no why to that. It's simply that's the way it's done. That's the way it's defined. Okay. You could have defined it the other way around. You could have defined the reactants on top and the products on the bottom. That would also become a constant value at equilibrium. But that's not how chemists have done it. So the traditional way to write a Kc expression is to put the product concentrations on the top, the reactant concentrations on the bottom, take the coefficients from the balanced equation and use them as the exponents in the expression. And when there's more than one concentration, to multiply them together in the expression. All right, so I hope that's clear. We're going to look at some examples in just a moment. All right, we're going to be using this Kc expression on the next slide. So in this next slide, we have a 1 liter flask. Okay, you're going to want to note that for yourself. And we're going to fill the 1 liter flask with different concentrations of hydrogen, iodine, and HI. Okay, we're then, through this animation that you're going to see on the screen, we're going to let the reaction go and reach equilibrium. when it reaches equilibrium, we'll be able to see what the concentrations are in the equilibrium mixture, and then we're going to calculate the Kc value together. Okay, so what you want to do is note that the volume is 1 liter. You want to note what the initial concentrations are when I start, and then we'll note what the equilibrium concentrations are. Okay, so you may want to create a little table for yourself so that we'll do experiment 1 together. Okay, in fact, let me no, I was going to switch cameras, but I'm not going to. I'm going to leave this here. All right, so I'm going to set the first experiment. So if you want to call this experiment 1, let's put, I'm just picking numbers randomly. I'm putting 4 moles of hydrogen. Now remember, the volume was 1 liter. So that means the concentration of hydrogen is now 4.0 molarity. Okay, we'll say 4.0 molarity. The iodine, let's put in 4 moles also. So the iodine is also 4.0 molarity. Remember that C, concentration, is equal to N divided by V. C is equal to moles divided by liters. So 4 moles divided by 1 liter is 4.0 molarity. Let's not put any HI in. So the HI will start off at 0 concentration. So now if I have hydrogen and iodine in the container and no HI in the container, then only the forward reaction will happen. So we expect the hydrogen and iodine to react and their concentrations will go down. As a result, the HI's concentration will go up. So let's let them react. I'm going to click the react button. So now you can see the concentrations down below are dropping for H2 and I2, while the concentration of HI is going up. And notice now the concentrations have all stopped changing, right? So they've all stopped changing. You want to, let me see here. You want to take these numbers at the bottom of the screen and put them as your equilibrium concentrations for hydrogen, for iodine, and HI. So for hydrogen, we now have 2.34 molarity at equilibrium. For iodine, we have 2.34 molarity at equilibrium, while at HI, we have 3.31 molarity at equilibrium. Okay. So I'm going to stop sharing this screen. Actually, I'm going to switch my screen to my document camera. Did that work? All right, I'm back to William. I'm looking at William here. All right, actually, you can see my screen now, can't you? You can see the.
Yes, I could.
Yes, I didn't realize that. I was looking at my I was looking at my own computer instead of my phone. Whoops, there we go. I'm going to stop sharing that again. All right, so here's what we have. So we have at equilibrium, we had concentration of hydrogen of 2.34 molarity. We had concentration of iodine at 2.34 molarity. We had concentration of HI at 3.31 molarity. So what we want to do is use these equilibrium numbers to calculate the Kc value for this reaction. So if you haven't already done so, just rewrite the Kc expression. So we have HI concentration squared over hydrogen's concentration times iodine's concentration. And remember, we have to use numbers at equilibrium when we substitute these into the expression. And again, feel free to ask me a question. I have Ms. Weens has just joined me in the room here. So she's here to see what it's like to run a Zoom meeting. So if you have a question about something, feel free to ask. So the HI concentration was 3.31 molarity. We're going to square that, divided by 2.34 molarity times another 2.34 molarity. Say again?
Mr. P, where did you get your molarity from?
So William, those were on the previous screen. If we go back to,
okay.
Those were the numbers at equilibrium, right? All right, so take your calculator and plug those numbers in on your calculator and divide, okay? So Queens is here. I'm just going to tell on the side of my computer, you can see all the students who are participating. We have 42 students in the lesson right now.
Wow.
2 sections of grade 12
Okay.
chemistry. So on my calculator, 3.31 squared divided by 2.34 squared, or divided by 2.34 twice, you should get that the, whoops, I just typed the wrong number in. 3.31 squared divided by 2.34 squared, I get an answer of 2.00. Did you guys get the same thing? I'll take your silence as yes. Okay, so 2.00 was our Kc value in this first experiment. But let's go back now and do a different experiment. Okay, so I'm going to go back to the PowerPoint presentation, and we're going to reset it. And in your notes, you can write now experiment number 2. Okay, so in experiment number 2, let's put different amounts of hydrogen and iodine. So this time I'm going to put 8 molarity. Remember, the volume is 1 liter, so 8 moles divided by 1 liter is 8 molarity. And then we're going to put 2 moles or 2 molarity of iodine in, and we'll put no HI in again. All right, so those are our new initial conditions. So the hydrogen is 8 molarity, the iodine is 2 molarity, and the HI is starting at 0 molarity. So now we'll let them react. And just like before, you notice at the bottom, the hydrogen is dropping, the iodine is dropping, while the HI is increasing. So that means the reaction was going in the forward direction. Notice the numbers at the bottom of the screen are now constant, and that means we've reached equilibrium. So write down those 3 concentrations again, and say this is for experiment number 2, and calculate the Kc again. So take those concentrations and put them into your expression. I'm going to switch over again so you can see what I'm writing, but make sure you're doing it yourself and then just checking to see if you've got the same numbers as me. Whoops, as I just wrote the wrong number. All right, so let me switch over. So what you should be saying now, I'm going to show Miss Wiz, this is what the students are seeing on their device. I've got my device muted right now, so nobody.
So they can't see each other.
I think they can if they switch here. I think there's a way that they can see.
I can see certain people. Like Asmat has his camera on.
You can switch to active speaker, or you can go to a classroom view, so it kind of goes to everyone, and then you slide to your right, and you can see everyone in the chat.
Right.
Ah.
So I'm on a mobile device, right? Yeah. So I'm doing that.
Yeah.
I'm doing that on my phone here as well. And when you swipe one way, even though I've muted microphones on a mobile device, you could just tap the button and ask a question. So we don't hear the constant noise of little papers moving or whatever, but someone can just tap and ask a question. So on your screen, you can see what I'm doing. And if you've grabbed your calculator, do you notice anything interesting about the answer? I get 1.99 this time, which is pretty much the same as 2. So notice that even though we used different starting conditions in these 2 experiments, even though we ended up with different equilibrium concentrations in the 2 experiments, when we calculate the Kc value for the 2 experiments, the answer is pretty much the same, 2.00, 1.99. That's why it's called an equilibrium constant, because it gives you the same result no matter how you did the experiment. As long as the temperature is the same. That's a very important point, right? The temperature has to be the same. All right, we're going to do one more experiment. This time we will do a reverse reaction. So let me reset the animation in the PowerPoint. This time, instead of putting hydrogen and iodine in the container, let's put just HI in the container. All right, I see there's somebody is sending me a chat message. I'm going to click on the chat message. What would be the units? That's a good question. In the rate laws that we were doing, when we calculated rate constants, we always specified that the units were critical. In equilibrium constants, for reasons that are beyond grade 12 chemistry and even beyond AP chemistry, for reasons that you don't really get explained until you're in a second year university chemistry course, the units for KC will always cancel out. They don't look like it usually. In this particular example, they actually do look like they cancel out because we have a molarity squared divided by a molarity squared. But of course, not all reactions will have stoichiometry that looks like it cancels out. The bottom line is the KCs don't have units. So we won't ever worry about the units for a KC value. But just be sure you're always using molarities when you're calculating them. Always put concentrations to find KC. So coming back to the animation, I put the HI initially as 6 molarity, and we're going to put the H2 and the I2 initially as 0 molarity. So now there's only HI in the container. There's no hydrogen and iodine. So this reaction cannot go forwards, right? There's no hydrogen or iodine, so there can't be a forward reaction. There can only be a reverse reaction. So as it reaches equilibrium, we're going to see hydrogen and iodine increase, and we're going to see the HI decrease. So let's run the reaction. There it goes, and you can see the HI has decreased significantly. The H2 and the I2 have increased significantly. Copy down those concentrations. When they're constant, you've reached equilibrium, and calculate the KC for experiment number 3. Any thoughts, Ms. Weems, on what you're seeing?
Looks pretty cool so far. I'm trying to think of how I can use this for my drama class. So
For a drama?
quite a different context.
Yes, yes. Well, I'm using writing under a document camera,
Yes.
but you could be using the webcam on your laptop, or we could use the document camera aimed upwards, and you could be acting something out
Yeah.
physically and videotape that. Of course, you could also just use it for conversation with a group. So some assignment that you've given, you could then just have a group conversation about it and talking to people and seeing them, and just that 10 or 15 minute touching base with a class each day, I think, if nothing else, would be good.
Yeah.
All right. So you guys have calculated the KC, I'm sure. I'm going to switch to my paper here. So you calculated KC the 3rd time with these totally different numbers again. Notice these numbers are totally different from before. Let me try something different here. Will, you're here today. Will, can you unmute your microphone and tell me what your KC is for this experiment?
It's 2.
I didn't
Oh
say
no, Will.
William. I said Will. What the hell,
Oh.
Will? William. Okay, Will Houston.
Hi.
Hey, what did you get as a KC value for this 3rd experiment?
I'm still typing it in because I got distracted.
Distracted. I mean, you didn't think the teacher was going to call on you, especially at home.
Here, 2.00.
2.00. There we go. So again, the 3rd experiment, different, this time only a reverse reaction happening. When it reached equilibrium, the numbers, the concentrations were all different concentrations than we had in the first 2 experiments. But when we plugged them into the KC expression, we got the same value as the first 2 experiments. So we see that it's called an equilibrium constant because it always gives the same value for equilibrium concentrations at a given temperature. If this were a different temperature of the experiment, then we would not get the same value for KC. All right, so the KC value depends on the temperature. All right, thank you, Will, for that response. Let's go back, and we're going to wrap up in just about 5 more minutes. Okay, so if you're getting a little bit bored at home, sort of like being in class. All right, so let's share the PowerPoint again. Okay, let's go to the next slide if I can.
I couldn't help but notice that one of your students had left the chat.
What? Probably gone to the bathroom maybe. And for some reason, my PowerPoint is no longer active. Let me just see if I can fix that. Boom. Okay. I'm going to switch over to this slide here. Okay. Sorry, folks, my computer may be a little bit tired of showing PowerPoint presentation. All right, you guys can see this slide now, I think. So let's, these are several reactions. I want you to copy the chemical reaction down. Do not skip that step. And then write down beside it the Kc expression. Okay, so I'll do mine on my paper. You can do yours on your paper and we'll compare answers. Remember the term homogeneous and heterogeneous equilibria. If it's homogeneous, it means only gases are present or only aqueous things are present. If it's heterogeneous, then there can be more than one phase. Now, there is something important about that. In a Kc expression, this is very important, so pay attention. In a Kc expression, we only include concentrations that can change. So gases, they can change their concentrations. If you have a given volume of gas and you create more gas in that same volume, the concentration goes up. Same thing with aqueous species. If you have a certain volume of a solution and you dissolve more material in it, its concentration goes up. So gases and aqueous species, their concentrations can change. But we talked about this in our kinetics unit. If you're a solid or a liquid substance, your concentration is constant, no matter how much of it is there. So when solids are used up in a reaction, the amount of solid goes down, but the concentration of the solid doesn't change. And the same thing would be true for liquids. You can produce a liquid, you can use up a liquid, so the amount will change, but the concentration of the liquid never changes. So for liquids and solids, because they have constant concentrations, we always omit them from the Kc expression. Never put a liquid or a solid in your Kc expression. Now, what if the liquid or solid was the only thing in the numerator or the denominator? In that case, you would simply put a 1. Okay, you have to put something there. So if there's only a liquid or a solid in the numerator or denominator, put a 1 in its place. All right? All right, so go ahead and try writing those Kc expressions, and then I will show you some of my answers, and then we'll call it a day.
It's how come a gas can change its concentration then?
So how come a gas can change its concentration? So imagine you have a closed flask, so nothing can get in or out, but you are doing a chemical reaction which produces hydrogen iodide gas, what we just talked about a minute ago. If you're producing more hydrogen iodide gas in that constant volume container, so you have more and more moles of HI in the same volume, then the concentration of the gas will go up. And so gases, you remember, have large spaces in between their particles. Gases are compressible and expandable. So you can put more gas in the container, its concentration goes up, right? Because the volume is constant. But if you try putting more liquid in a container that was already full of liquid, you can't, right? The liquid cannot be compressed. Liquids also don't expand appreciably. So therefore, the concentration of a liquid and a concentration of a solid are constant, okay? Gases and aqueous things, they can be compressed gases or expanded gases. You can dissolve more or you can dissolve less of aqueous things, so their concentrations are changeable. Okay, I hope that helps. So you're writing the balanced equation down, and then beside it, you're writing the Kc expressions. I'll show you my first 2 answers in just a moment, so you can make sure you're doing it right. You don't want to make a whole bunch of mistakes. All right, so I'm going to switch cameras here, and you can see my answers to the first 2 of those. I'll give you another 30 seconds or so if you haven't done them. All right, so there's my answers for the first 2. So the product concentrations, the things that were on the right side of the chemical reaction, are in the numerator. The reactant concentrations are in the denominator. When there's more than one reactant or more than one product, I'm multiplying their concentrations. And I'm using the coefficients from the balanced equation as the exponents in my expressions. So double check, make sure you're writing those. And if you're not understanding, now's the time to ask. I will take that as we are understanding. So let me go back to the PowerPoint. All right, so go ahead and try the last few questions and then we will call it a day. There will be an assignment on Edmodo, so check with that later. It'll be due on Monday. You'll have the weekend to get it done. In the third example, notice there's fractions involved. That doesn't matter. Fractions, if you've taken a math class in high school, you know that exponents can be fractions. When you raise something to the power of 1/2, you are square rooting it. So one more time, be sure you're writing the balanced equations down. Otherwise, when you look at your answers later, they'll be meaningless. If you don't have the balanced equation, the Casey expression by itself doesn't mean anything. Okay, when you get to the fifth and the sixth examples, those are heterogeneous equilibria. There's liquids, solids, and gases. Remember to leave out liquids and solids from the Casey expression.
Mr. P, are we gonna go over the test of yesterday?
William, I decided I was going to wait for that, okay?
Okay.
There was an issue last night. A good movie came on and I didn't finish marking them.
Well, at least he's honest.
Exactly. So the fifth example, the products, one of them is a solid. I'm going to leave it out. The carbon dioxide is a gas, so I'm going to include that and raise it to the power of 3. Now notice in that example, there are no reactants that I'm going to include. The reactants are solid, that's it. So I don't have to write divided by 1, but you could. If you want to put the CO2's concentration cubed divided by 1, you could, but to divide by 1 doesn't do anything. So you could just write CO2 cubed. And the last example has 2 things in it that will be included. We'll have the concentration of the carbonic acid and the concentration of the CO2. All right, can I show you my answers before we end here? Anybody still need more time? Do I take silence as meaning I can go ahead?
Yes.
I'll give you another 1 minute. I'm not writing the balanced equations in my answer, so I'm going a bit faster than you guys. My intention, you guys, will be, if possible, to run just 1 class per day. But if I have to, we'll go to 2 classes a day if there's conflicts. But I intend, in addition to the 1 class per day like this, a 30, 45-minute lesson, I'm going to offer a 30-minute, 45-minute help session. So once a day, I'll put it on Edmodo, but once a day, if you had trouble with the homework or didn't understand something earlier with 40 some odd people, didn't want to ask, you could come to that small group, smaller session. There should only be a few people, I hope, at those sessions and get some more one-on-one kind of help, okay? Of course, you could also request a one-on-one meeting like this if you want to go over something specific, but I'd prefer to do it with smaller groups of people so I don't have to answer the same questions repeatedly. All right, I'm going to stop sharing the PowerPoint and show you my answers. So double check your answers. So number 3 with the fractional exponents. 4 was more straightforward. And then 5 and 6 with the heterogeneous equilibria. Are there any questions about those? So we're leaving out liquids, we're leaving out solids. In number 5, the denominator had a solid in it, so I just left it out. If your numerator had only liquids or solids, then you would need to put a 1, right? If there's a numerator with nothing in it, you have to put a 1 there. But if there's a denominator with nothing in it, you can leave out the 1, right? To divide by 1 doesn't do anything.
Wasn't the CO2 a reactant though in the thing?
So the CO2 in the 6th one?
The 5th one.
The 5th one. The 5th one, the CO2 was a product, I thought it said. Can anybody else confirm that, or do I need to go back and look?
No, I was looking at the wrong question. Never mind.
How about
Yeah, in the 5th one, the CO2 was a product. Aluminum carbonate was decomposing, right?
You can include aqueous solutions then, and
Yes, so you include aqueous things because aqueous things are dissolved in water. You can dissolve more or you can dissolve less. Their concentrations change. And gases also can change. So you leave out liquids, you leave out solids. All right, so folks, thank you on a Friday. There's a little bit longer than I had intended, but thank you guys very much. How was the experience? Was it doable for you?
ask yourself, guys?
Yeah.
it was good, yeah.
It was doable.
All right.
Shippy, I have a question.
Yes, William.
The last one, I thought the reactant was the
Sorry,
only.
William. I'm just going to point out that for everybody in the future who's getting tired of hearing William ask question after question, in the future, William will be limited to 2 questions, after which there will be $1 per question. All right.
Hey, 2 questions only. Fine, whatever.
What's your question?
The last equation there, right? I thought it's only the reactant that. It's only the reactant.
So in the last example, if you go back and look at the balanced equation,
Yeah.
product with aqueous carbonic acid, H2CO3. So because it's aqueous, we can include it. It goes in the numerator.
Oh, okay.
CO2, which was a reactant, the CO2 reactant was gaseous, so we can include it. But the water was liquid, and the water liquid we leave out, right? So we included the H2CO3 in the numerator because it was a product and it was aqueous. And the denominator, we included CO2 because it was a gas, and gases get included. All right?
Thanks.
All right, I'm noticing that there's some chit chat going on. I don't see, it says, will you be at school after lunch so I can pick up homework for the next 3 weeks? If you did not pick up the equilibrium package of materials, I will be here at school until 3:30 today. If you come after 2 o'clock, I'll be doing a live session, but my door will be open. You can come in and just pick up the package. I also posted the package of worksheets on Edmodo, so you could also print them at home if you like. So starting on Monday, we'll do an 11 o'clock session again, and we will need the package of material that I'm giving you. Okay, so on Monday we're jumping into that package. All right, folks, thank you guys very much. I hope you're surviving the apocalypse. Okay?
Mr. P, last question.
Yes, William, last
Oh my god.
Danny's asking for the
Well, you're
Edmodo
probably
code.
wondering, if you're probably wondering, looking at my amazing hair, you're wondering, did I get a haircut? And the answer is yes, I got a haircut. And I'm glad I did, because my barber, when I got there, said she's probably going to be no longer doing hair for the next who knows when. So I told her to cut it extra short, as you can see. So I should be good. William, what's your question?
My question is like Danny's asking for the Edmodo code.
Dan needs the Edmodo code.
Oh no. Oh no. That's actually a bra moment there.
We'll wait for that.
No, Danny
a proud
just
moment.
sent me an email. Our Edmodo code was using lowercase letters. It's the letter C, the number 5, the letter I, and then B is in Bob, B is in Bob, and then the letter Z. So C5I, B, Z.
BBZ. Thank you.
If there's a problem with that, just message me on Edmodo and I'll get you another code, okay?
Sure.
Folks,
Thank you.
have a great
Thank
weekend,
you for letting me
everybody.
join you guys.
Okay? Take care.
You too.
Bye.
Bye.